Howdy, lads and ladies. Welcome back to Calc 2. Sorry for the delay. I'm still having some troubles with Zoom's single sign-in feature, but hopefully it won't cause any more headaches today. So you all completed your tests. Of course, I have not graded those yet, but I will get them back to you by next Tuesday. That's the usual rule. I do think there are some people who still need to take the makeup test. So if you haven't taken the exam, you need to reach out to me like immediately so we can get that knocked out. That's super important. I don't really care why you missed it. I just want you to take it. Of course, it won't be the same test. It'll be a makeup test, slightly different. But today we're going to move on. So while I still have you guys thinking about series, and now that you are all, at least hypothetically, masters of convergence testing, we're going to talk about something called power series, which is sort of the payoff, the reason that we talk, sorry, this is section 4. The payoff or the reason why we talk about series in the first place. So this is MAC2312, section 004. It's a lecture. And today is the 8th of April, 2021. And this is the bad pen. All right. So, today, we begin talking about power series. It is the case that we're in a bit of a time crunch. I'm sure, as you are all aware, the semester does not have a whole lot more to it. We've got next week and then the week after that. And that's pretty much it, lads and ladies. The last day of class, I believe, for you guys is the 23rd or 22nd. 23rd is the last day. That's a Friday. So we've only got a couple weeks left, which means we got to move kind of quickly here. And I'm going to do my best to make this digestible. And not to push anything out that is important. So a good treatment of power series is crucial. Today we're going to cover section 11.8. And there's a homework that I published for you earlier today that is going to be due next Tuesday. And it's just the 11.8 stuff. 11.8 is just like the introduction to power series. What is a power series? Basic definitions, radius of convergence, that sort of stuff, which we will talk about today. That's going to be next Tuesday, so that we can move through 11.9 and 11.10 next week. And then we'll be done with power series. So it's going to be like a week and a half of power series, as we said in the Discord. Following that, we'll have about a week to talk about some applications, which will mean like parametric equations, polar coordinates, some concepts like arc length, surface area. So the very last week will be soft, but the remainder of this week and next week, we're pushing hard, and the concepts are challenging, make no mistake. So I don't want to waste any more time. Motherfucker. All right, definition. A power series is an expression of the form A0 plus A1 times x minus A plus A2 times x minus A squared plus A3 times x minus A cubed, and so on. Actually, I think your book uses C's here because they don't want you to get confused between the A's and the here. So yeah, we can C1, C0, C2, C3. In sigma notation, you'd write this as the sum from 0 to infinity of Cn times x minus A to the n. And I'm going to go ahead and give this thing a name. I'm going to call it f of x. Because you'll notice it's a function of of x, right? There are x's in here. So it's an infinite series where you've got this variable x inserted. The CNs here are called coefficients. So the numbers C0, C1, C2, and so on are called coefficients. And the number A is called the center. Yeah, so I apologize for the notation. Call this C0, C1 times x minus a, C2 times x minus a squared, C3 times x minus a cubed, and so on. It's a polynomial. These are infinitely long polynomials. That's really what they are. You've actually seen some of these in the past. Before I get into examples here, let me just state a little fact. Associated with each power series is a number, call it capital R, and it's always greater than or equal to 0, called the radius of convergence. And associated and with each power series is an interval I called the interval of convergence. Such that if x is in the interval I, then the power series converges. And if x is not in the interval I, the power series diverges. And as you may suspect, these two facts are connected to one another. And we'll see the explicit connection in a moment. But basically, power series converge or diverge depending on what you plug in for x. You plug in A for x, for example, if I were to plug in the center, then this piece would be 0. So this series would actually just have one term. Everything else would be 0. So of course that's convergent. But if you plug in like something big for x, then this piece might be quite large and might make this whole series diverge. So the convergence here depends on what you're trying to plug in for x. And the set of all x values that you can plug in and still get a convergent series, that's called the interval of convergence. And then the radius of convergence turns out to be the radius of the interval of convergence, but we'll see that. We don't know that just yet. just a second. Okay, so let me show you an example. One power series we've seen. Let's find the interval of convergence oh, wait. Let me see here. I need to give you something else here. I'm sorry, such that the series converges provided the absolute value of x minus a is strictly less than r. Yeah, I'm so sorry. So we need to add this bit at the end of the radius of convergence fact here. So called the radius of convergence such that the series converges provided the absolute value of x minus a, so x minus a on absolute values, is strictly less than r. I'm sorry, without this, we don't really know what the radius of convergence even means. And so you can kind of unpack this inequality to find your interval of convergence. It turns out to be slightly more subtle than that, but not much. Okay. So an example of a power series we've seen. This one. I'd like to make a few comments along the way here. The CNs, the sequence of coefficients here, it's just 1 for all n. All right, and the center A here is 0. In other words, you can think of this series as sigma n from 0 to infinity 1 times x minus 0 to the n. But nobody would write this. This kind of looks silly. Everybody would just write this. But, you know, if there's nothing there, that means it's like 1 times that thing. And x to the n is the same as x minus 0 to the n. So these are your CNs. And this is your center A. Now you had some problems like this in your homework, only we didn't phrase it this way. We just said find all the x's such that a series like this converges, right? You guys remember that? So the simplest way to do this would be to run the ratio test or the root test, or in this case, we could actually make an argument following from geometric series. But generally what you're going to do is run the ratio test. This whole thing here is your AN, right? So if you run the ratio test here, you'll have x to the n plus 1 over x to the n. Which is the limit as n goes to infinity of the absolute value. Well, when you cancel these, you just get absolute value of x. And this doesn't have any n's in it. All the n's go away. So here you just get out absolute value of x. Since L is equal to the absolute value of x, the series will converge. Converge, I could say converge absolutely. Provided L is less than 1, which is equivalent to saying the absolute value of x is less than 1, because L is the absolute value of x. And that's equivalent to saying that -1 is less than x is less than +1. So this is what we call unpacking an absolute value inequality. The rule here, the absolute value of some shit is less than a constant, means the negative version of that constant is less than that shit is less than the positive version of that constant. So that's the rule I'm using to go from here to here. So I'm guaranteed that this series will converge as long as x comes from the open interval -1 to 1, i.e. the power series sigma n from 0 to infinity x to the n is, I always misspell the word guaranteed, guaranteed to converge absolutely, which is the type of convergence we most like, as long as x is in the interval -1 to 1. This is what the ratio test, when applied to this series, tells me. In general, power series, the ratio test will always give you an open interval when you apply it to a power series. After you find that open interval, you need to check the endpoints. You need to see whether the series will converge when you plug in this example, -1 or +1. So at x equals -1, the series becomes sigma n from 0 to infinity, -1 to the n, which diverges by TFOD. And at x equals +1, the series becomes sigma n from 0 to infinity 1 to the n, which also diverges by TFOD. Therefore, the interval of convergence for the power series sigma n from 0 to infinity x to the n is the open interval, call it I, and it's -1 to 1, the open interval from -1 to 1. In general, this is how you find the interval of convergence for any power series. You run the ratio test. L will come out to a function of x. It'll be usually the absolute value of x times some number. then you solve the inequality L is less than 1, because you know that series converge as long as L from the ratio test is strictly less than 1. It's a sufficient condition. It's not necessary, it's sufficient. So here we solve that inequality using this unpacking rule for the absolute value. And that tells us -1 is less than x is less than +1, which is the same as saying x is in the interval, open interval -1 to 1. The ratio test will always give you an open interval. Following that, you need to check the endpoints. So I can even add it here as a separate step. We'll say endpoints. These are the two steps for finding the interval of convergence. The radius of convergence is the distance from the center to the edge of the interval of convergence. Okay, now in this example, I just wanted to find the IOC, the interval of convergence. That's all we asked for. So we have done that. We've done that successfully here. The interval of convergence is the open interval from -1 to 1. I want to talk about what it means for a power series to converge, to try and give you a little bit of a picture. To do that, I want to look at the partial sums for this power series. I'm going to wait just a second in case anybody's still writing, and then I'm going to turn the page and do just that. Five seconds. The first partial sum, for reasons I'll explain later, we call the partial sums T. T0, T1, T2. T stands for Taylor. Like I said, I'll explain later. T0, if you sum this from 0 to 0, you just get 1. T1 is 1 plus x. T2 is 1 plus x squared. T3 is 1 plus x squared plus x cubed. Right? The full version of this series, this is 1 plus x squared plus x cubed plus x to the 4 and so on. Right? If you write out all the terms, it's just x to the 0 plus x to the 1 plus x to the 2 plus x to the 3 plus x to the 4 and so on. So what does it mean to say that this series is converging? If each partial sum is a function of x, what does it mean to say a sequence of functions converges? It's a whole different ballgame. But it turns out you can kind of think one point at a time. You think one x value at a time. The best way for me to show you this is going to be in Desmos. All right. 1 plus x. 1 plus x plus x squared. 1 plus x squared plus x cubed. The next partial sum is 1 plus x squared plus x cubed plus x to the 4. Next one is that plus x to the 5. The next one is that plus x to the 6. Undoubtedly, this looks kind of confusing. Let me make these all the same color. That might make things a little bit more confusing at first, but I want you to hold on to your hats for a second, because this is about to get pretty cool. All right. I said that my interval of convergence is the interval from -1 to 1. So in addition to each of these, I'm going to restrict. Actually, you know what? Fuck that. We'll just leave it. Here. I'm going to graph one more function. Where is this display anymore? Oh no. Oh, that's fine. I'm going to graph one more function here. I'll put it in red. And I'm going to take away a bunch of these and then slowly add them back. Look at this red function and pay special attention to the interval from -1 to 1. Watch what the blue functions do. This is T0, right? T0 is just 1. It's the 0th partial sum. Here's the first partial sum. Here's the second partial sum. Here's the third partial sum. Here's the fourth partial sum. The fifth partial sum. The sixth partial sum. What is happening?
They're alternating?
Looks like you're getting pretty close to the red function.
Yeah. These blue functions are getting closer and closer to the red function. Look here, the 8th partial sum. If I zoom in and I just look like here, I can't even tell the blue and red apart. They look exactly the same, don't they? The blue functions, as I add more and more terms, as I look at larger and larger partial sums, get closer and closer to this red function, especially if I restrict my attention to the open interval from -1 to 1. We'll run through that just one more time. Look at this red function, the 0th partial sum, the first partial sum, the second partial sum, the third, the fourth, the fifth, the sixth, the seventh, the eighth. So suppose, for example, I wanted to find the area under the red curve from like -1/2 to 1/2. Would you agree that that's probably really fucking close to the area under the blue curve here from -1/2 to 1/2? I can't even tell a difference. As you get closer and closer to the end of the interval of convergence, remember -1 is the left endpoint for the interval of convergence of this power series, there the blue and the red start to diverge from one another. But as long as you stay close to 0, which is the center of this power series, the red and the blue are indistinguishable. This is what it looks like for a power series to converge. In this particular case, here we see the polynomials Tn of x getting closer and closer to the function f of x equals 1 over 1 minus x. This is what it means to say that the power series sigma n from 0 to infinity x to the n converges to 1 over 1 minus x. As long as x is coming from that interval of convergence, as long as x is between -1 and 1, this polynomial will get closer and closer to this function. And the more terms you use, the closer it gets. Right? Just look at these last few. The more terms I use, the smaller the vertical space at any particular x value becomes between the blue function and the red function. This is what it means to say that this power series converges to this function. Now we're lucky in this particular problem in that we could have discovered, using what we know about geometric series, that 1 over 1 minus x is what this function will converge to. Note here, sigma n from 0 to infinity x to the n is a geometric series. So we know that if it converges, and in that case, that means, i.e. -1 is less than x is less than 1, then it will converge to the starting term divided by 1 minus the common ratio. And here, the starting term is 1, right? The first term of this series is 1 over 1 minus the common ratio is x. So 1 minus x, that's it. So a power series is a series that has a variable in it. It's an infinitely long polynomial. Whether or not that series converges depends on what you're trying to plug in for that variable. This power series converges if you plug in any number between -1 and 1. So you can think of this as a function. The number to which this series converges depends on what value you plug in for x. That's what a function does. You feed it an input, it gives you an output. Here, you plug in a particular number x, and as long as that number is between -1 and 1, this series will converge to 1 over 1 minus x. So you feed this thing 1/2, the series will converge to 1 over 1 minus 1/2. You feed this thing 1/3, the series will converge to 1 over 1 minus 1/3. It's a function. It's just a function that's expressed as a power series, and that's the big deal. The long-term question here is, what functions can we express as a power series? And if I give you a function, how can you write it as a power series? But before I start pushing you on those questions, we need to get really comfortable with this idea of finding that interval of convergence, right? This whole picture, I can only think about and draw this picture because I know to pay attention to the interval -1 to 1. If I was looking somewhere else, the blue functions wouldn't be getting closer to the red function, and I wouldn't see this pattern. Right? If I was zoomed in on like +5 over there, I wouldn't see any connection between the blue and the red. So, some information about convergence of power series. we've defined what the interval and radius of convergence are, but I want to help you see them. So intervals and radii of convergence. A power series centered at A, something like sigma n from 0 to infinity, Cn times x minus a to the n, will always have an interval of convergence whose endpoints are a minus r and a plus r. In other words, the IOC, the interval of convergence, is always symmetric about the center. You know, if here's the number a, the center of my power series, then a plus r would be over here, and a minus r would be over here. So the distance from the center to the endpoint is always r. That's why we call it a radius of convergence. This is the one-dimensional analog of a circle. And if you study these things in terms of complex variables, then you actually do get a circle of convergence, a disk of convergence. There are some fun questions that can be asked about possible intervals of convergence. Like if you have a power series centered at 2, is it possible that the IOC is like -5 to 3? The answer is no, because that interval is not symmetric about 2. So kind of the simple way to think of this, i.e. intervals of convergence are always symmetric about the center. All right. So if I ask you for the interval and radius of convergence, you should run the ratio test. That will give you an open interval. You can look at that, you can draw that open interval, mark off the center, and find the radius of convergence. It will be the distance from the center to the endpoint. Then to find the exact radius or the exact interval of convergence, you need to test the endpoints as well. Another neat fact here. Intervals of convergence will always be one of a minus r to a plus r closed, a minus r to a plus r left open right closed, a minus r to a plus r left closed right open, or a minus r to a plus r open on both sides. And one must test the series at both endpoints to determine the exact interval of convergence. So you run the ratio test. That will give you always the open interval. That open interval will look like this. Separate from that, you need to plug in those endpoints and see whether your series converges or diverges at those values. If your series converges when you plug in the left endpoint, then your interval of convergence is closed on the left. It's either this one or this one. Because remember, the interval of convergence is the set of all x values such that your series converges. Let's look at another example. Find the radius and interval of convergence for the power series sigma n from 0 to infinity -1 to the n x to the n over 2 to the n times the square root of n plus 1. This is a power series. The coefficients and center we should figure out. So I'll try to rewrite it in that form that we saw in the definition. The coefficients here are everything except for the x stuff. So this is -1 to the n over 2 to the n times the square root of n plus 1 times x minus 0 to the n. So these are my coefficients, Cn, and the number a is equal to 0 here. The center is 0. Is everybody with me? So asking what are the coefficients and what is the center? Those are sort of the simplest questions I can ask about a power series. If I want to find the interval and radius of convergence, I start with the ratio test. L is always the limit as n goes to infinity, absolute value of an plus 1 over an. And remember, an is just everything inside the sum. So this is limit n to infinity, absolute value of, I'll do it like this, just once, -1 to the n plus 1, x to the n plus 1 over 2 to the n plus 1 times the square root of n plus 1 plus 1. There's an plus 1. And then an is -1 to the n, x to the n over 2 to the n times the square root of n plus 1. Obviously, we need to clean this up quite a bit. So this is lim n to infinity, absolute value of -1 to the n plus 1, x to the n plus 1 over 2 to the n plus 1 times the square root of n plus 2. And now I flip this guy and bring him upstairs. So I'll have 2 to the n square root of n plus 1 divided by negative 1 to the n x to the n like this. And now, just like when you run the ratio test on any other series, you're going to want to group like pieces together. So I've got x's, negative 1s, 2s, and square roots. So the x's, x to the n plus 1 over x to the n, times the negative 1s, I've got negative 1 to the n plus 1 over negative 1 to the n, times the 2s, 2 to the n over 2 to the n plus 1, and the square roots, square root of n plus 1 over the square root of n plus 2. Everything in absolute values. Simplifying. You get lim n to infinity, absolute value of x times negative 1 times 1/2 times root n plus 1 over root n plus 2. And I can take the absolute value of each of these things separately, right? Absolute values are multiplicative. The absolute value of negative 1 is 1. The absolute value of 1/2 is 1/2. The absolute value of root n plus 1 over root n plus 2 is just root n plus 1 over root n plus 2. The only place where this absolute value actually has meaning here on these two pieces. So we get lim n to infinity, absolute value of x times, this is just 1 times 1/2 times the square root of n plus 1 over the square root of n plus 2. And we can pop this piece out of the limit. So I'll have the absolute value of x over 2 times the limit as n goes to infinity. Then I can write this as a single square root n plus 1 over n plus 2. I'll give you a second. Once you've caught up, I'd like you to tell me, what is this limit? Just this part. Yeah, Natasha nailed it in the chat. That limit is 1, right? N plus 1 over n plus 2. The inside there is going to 1. So this is the square root of 1, which is 1. So altogether here, I get the absolute value of x over 2. Because this limit is right here. It's just 1. Okay. Let me take this information over here. Since L is equal to the absolute value of x over 2, our series will converge provided L is less than 1, i.e. the absolute value of x over 2 is less than 1. L being less than 1 is the same thing as saying the absolute value of x over 2 is less than 1 because L is the absolute value of x over 2. Now we solve. This is equivalent to saying the absolute value of x is less than 2. Just multiply both sides by 2. And then I can unpack. And I get -2 is less than x is less than 2. But that doesn't mean that that's my interval of convergence. We said this is a sufficient condition, not a necessary condition. We need to now check the endpoints. In other words, what I know at this stage, therefore, the interval of convergence is one of -2 to 2 closed, -2 to 2 left open, right closed, -2 to 2 left closed, right open, or the open interval of -2 to 2. And the radius of convergence we can sort out at this point. My center, remember we said way back at the start, my center I know is 0. So here's my center. And my endpoints are -2 and 2. So the radius of convergence here has to be this distance, 2. So we can conclude that. We can say that the radius of convergence is r equals 2. If you compare the definition of the radius of convergence to this expression, you'll recognize it as 2 right away, right? The radius of convergence is the number such that the absolute value of x minus a less than r guarantees convergence. So this is the absolute value of x minus 0. 0 is the center, is less than 2. So the radius of convergence has to be 2. When you get to this step, you can recognize your ROC immediately. But if you're having any doubts, I recommend drawing the picture. All right, draw your number line with your center and the endpoints of your IOC, your interval of convergence. The distance from the center to either endpoint, doesn't matter which one you use, because these are always symmetric, is the radius of convergence, in this case 2. If you draw your IOC and your center and it is not symmetric, you made a mistake and you need to go back. So how do I determine which of these 4 possibilities is my actual interval of convergence? I test the endpoints. So that was all the ratio test work. Now I test endpoints. At x equals -2, we have, if I plug -2 into this series, sigma n from 0 to infinity, -1 to the n times -2 to the n over 2 to the n times the square root of n plus 1. Which is, we're just going to do some algebra now. Sigma n from 0 to infinity, -1 to the n times -2 to the n is -1 to the n times 2 to the n over 2 to the n times the square root of n plus 1. Fact I'm using here, -2 to the n is the same as -1 times 2 all to the n is -1 to the n times 2 to the n. That's how I split this piece up into these two pieces. We can cancel the 2 to the n's. And these two form sigma n from 0 to infinity, -1 to the 2n over the square root of n plus 1. And -1 to the 2n, since 2n is always even, or you can think of it as -1 squared to the n, is 1 to the n. It's just 1. So this is equal to sigma n from 0 to infinity, 1 over the square root of n plus 1. Does this series converge or diverge? This series.
Diverges?
It diverges. And there's a few ways to see it. The simplest way to see it is to rewrite it with starting index 1, right? This is 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3, and so on. You can actually rewrite this as a p-series. This is sigma n from 1 to infinity, 1 over n to the 1/2. Right, the plus 1 under the square root here, starting at n equals 0, gives me 1 over root 1, and then it's just 1 over root 2, 1 over root 3. This is called an index shift, where you rewrite it with a different starting index. This is a p-series with p equal to 1/2, which is not bigger than 1, hence diverges. So -2 is not in our interval of convergence. You see why you need to be so good at this convergence testing stuff, right? Each one of these power series has 3 convergence tests built in. The ratio test, which gives you your shape of the interval, the endpoints. And then you're going to have to do 2 more, 1 for each of the endpoints. So we just tested the first endpoint. We found that -2 is not in our IOC. That means any one of these that contains -2 has to get kicked out. Can't be either of those because both of those contain -2. On the other side, at x equals +2, we have sigma n from 0 to infinity, -1 to the n times 2 to the n over 2 to the n times the square root of n plus 1. And right away, the 2 to the n's cancel. So this is the alternating version of the series we were just looking at. This is sigma n from 0 to infinity, -1 to the n over the square root of n plus 1. What do we think about this series? Does this converge or diverge?
Converges. It's an alternating series.
Very good. This converges by the alternating series test. It's conditionally convergent. The convergence is weak because we know if you take absolute values, you get this guy again. But this guy is convergent by the alternating series test. And this is the level of rigor I'm requiring from you guys. When it comes to testing the endpoints on a power series, You need to tell me whether or not the series converges or diverges, and you need to tell me why, but I'm not going to require you to show all the details. This is why I like to break exam 2 right there. Up to exam 2, every time you convergence test a series, you need to show me all the details. But at this point, I am willing to believe a little bit that you know what you're doing. So if you can tell me that this converges by the alternating series test, I will believe you. And if you can tell me that this series diverges because it can be rewritten as a p-series, I will believe you. But if you get it wrong, it's no point, right? So this converges by the alternating series test. If you want to check the details, you can. Here, Bn is 1 over the square root of n plus 1, which is decreasing. Because the square root of n plus 1 is increasing. And lim n to infinity Bn is lim n to infinity 1 over the square root of n plus 1 is 1 over infinity is 0. There you go. There's all the details. The upshot is plus x equals positive 2 is in our interval of convergence. So the IOC, the interval of convergence, I is which one? Negative 2 is not in it, but positive 2 is. So this one does not include positive 2. It's got to be this guy. The left open, right closed interval from negative 2 to 2. That's my interval of convergence. So we found the radius and the interval of convergence. We have answered the question. It's quite a bit of work, no? Ratio test will tell you the radius of convergence. That, together with your center, will tell you what the interval of convergence looks like, right? It'll tell you what the endpoints are. Then you have to separately test each endpoint. That will tell you your exact interval of convergence. What does this mean? It means if I plug any of the numbers from this interval into my series, I will get a convergent series. That's what it means. So if I take any numbers from the left open, right closed interval negative 2 to 2, like negative 1 or negative 3/2 or positive 1.7, if I plug any number from this interval into this series, the result will be a convergent series. In other words, if you want to think of this series as a function of x, this is your domain. These are the x's that you're allowed to plug in to this series. All right, how are we doing on time? Doing good. There are a handful of other very special examples that I want to show you. One of them you've already worked with. I'll give you a second. Anybody needs to continue writing the details here. Little bits. Same game, new series. some of you in your study guide assumed that this series converges for all values of x. So I want to show it. I'm going to abbreviate IOC and ROC for radius, interval and radius of convergence, because I'm going to run out of ink if I don't. For the power series, sigma n from 0 to infinity, x to the n over n factorial. Again, because we're trying to get comfy with this new type of series, I think it's wise to write out the first few terms. So the first term of this series is x to the 0 over 0 factorial. That's 1 over 1, or 1. The n equals 1 term from this series is x to the 1 over 1 factorial. That's x. The n equals 2 term for this series is x squared over 2 factorial, which is 2. The n equals 3 term of this series is x cubed over 3 factorial, which is 6. And it continues on like this. And you see again, it looks like a polynomial, right? If I stopped it here, it would be a polynomial. If I stopped it here, it would be a polynomial. It's just a polynomial that goes on and on and on forever. That's what power series are on an intuitive level, infinitely long polynomials. Okay, I want to find the interval and radius of convergence, so I need to run the ratio test. Ratio test is generally your buddy here, although you could use the root test also. This particular series, the root test is hard because of the factorial, but in general, you could use the root test if you wanted to. Ratio test says, let L be the limit as n goes to infinity of the absolute value an plus 1 over an, which in this case is the limit as n goes to infinity, absolute value of an plus 1 is x to the n plus 1 over n plus 1 factorial. And I'm going to divide by an by multiplying by the reciprocal. That's always our next step, so we might as well just do that. Here, I get lim n to infinity. Absolute value, again, I'll shuffle the terms. So I have absolute value x to the n plus 1 over x times n factorial over n plus 1 factorial. And like one of your exam questions, you need to be comfortable canceling factorials appropriately.
Hey, Professor, could you slow down a bit? I'm having a little trouble writing this all down.
Sure.
Appreciate it.
Sure, yeah, tell you what, let me fill up my coffee. You guys can catch up here. So we know that n factorial over n plus 1 factorial is n factorial over n plus 1 times n factorial. The n factorials cancel and we get 1 over n plus 1. And we know that x to the n plus 1 divided by, oh, I'm sorry, x to the n here. This is an x to the n. We know that those cancel to x. So here I get the absolute value of x times 1 over n plus 1. As we did on the last one, we can split up the absolute values. Absolute value plays nice with multiplication. I can pop the absolute value of x out of the limit. And this 1 over n plus 1, that's positive, so I can forget about the absolute value there. What is the limit as n goes to infinity of 1 over n plus 1? Yeah, thank you, Matthew. Yeah, this piece is going to 0, right? The bottom's going to infinity, 1 over infinity is 0. So something funny has happened here. I get the absolute value of x times 0. And we know the series will converge provided L is less than 1. But here, L being less than 1 is the same as saying the absolute value of x times 0 is less than 1. What's the solution to this inequality?
Any x value, right?
Yeah, I could plug in x equals 10 million. I could plug in x equals Graham's number. I could plug in x equals the number of galaxies in the universe raised to the number of atoms in the universe. And I would still get a true statement because we're going to multiply that son of a bitch by 0. In other words, this is the same as saying 0 is less than 1 independent of x. So L is less than 1 for all real numbers x. Works for complex numbers too, but that's all we care about here is real numbers for all real numbers x. So what does my interval of convergence look like?
Negative infinity to infinity.
Good. So we'd say, therefore, the series sigma n from 0 to infinity x to the n over n factorial converges for any x in negative infinity to infinity, i.e., the interval of convergence is negative infinity to infinity, and the radius of convergence is r equals positive infinity. This is a special series. And I want to look for a second at the partial sums of this one as well. I'm going to do this with one more series. We're going to go a little bit over our normal time, but then we're going to stop. So no separate lab today. I want to show you guys this stuff and then turn you loose on the homework, because I want you working on this homework as soon as possible. Again, I said it at the start of class, just again, there's a homework that opened today, earlier today, I made it this morning, and it is due Tuesday at the start of class. I know. it's just this stuff. It's just finding intervals and radii of convergence, nothing crazy. But you need to practice it, and we need to get you comfy with this in time so we can actually do shit with power series next week. So this homework set is a narrower time gap than usual. Like I said, I want you to start getting a picture in your head of these things as well. So, oops, sorry, not zero. The first partial sum, second partial sum. Let me just, the next partial sum. Next partial sum. Oh, I should just, should just copy paste, shouldn't I? The next one is x to the 4 over 24, because 4 factorial is 24. And then x to the 5 over 120. And then x to the 6 over, oh, did I skip something? Factorial 4 factorial is 24, 5 factorial is 120. Yeah, no, this is 720. One more. I don't actually know what 7 factorial is off the top of my head, but here we go. All right. Let's play the same game we did at the very start. Here is the 0th partial sum. Here is the first partial sum. The second, the third, the fourth, fifth, the sixth, and the seventh. Now, if I just showed you this part, you would say this is what? Every calculus student's favorite function. Yeah, it's definitely some sort of exponential. And if we look at the output when x is equal to 1, it looks like we're a little bit, somewhere right around 2.5. This is e to the x. And again, I think it's worth watching these Taylor polynomials is what they're called, the partial sums. It's worth zooming out and watching these converge to e to the x. The first, yeah, Maclaurin or Taylor, same thing. Yep. The first partial sum, aka Taylor polynomial or Maclaurin polynomial, the partial sum associated with n equals 0, is the unique constant function that matches with your function at the center. So this is centered at 0. Does anybody recognize this? There's another name for this partial sum, aka Taylor polynomial, aka Maclaurin polynomial. The order 1 Maclaurin or Taylor polynomial. What does this blue line look like with respect to this red function? Yeah, it's the tangent line. The first order Taylor polynomial, or the first order partial sum for a power series, is always the tangent line. The second order is called the tangent parabola. It touches that function at the center. It has the same first derivative at the center and the same second derivative. So we call it the tangent parabola. It has the right slope and the right curvature at that point. This guy would be the tangent cubic, tangent fourth order, tangent fifth order, and so on. And again, you see the blue getting closer and closer to the red. And if you let me take these partial sums out further and further, the blue will get closer to the red everywhere because the interval of convergence here is all real numbers. It will take some time, but you see already, everywhere from certainly like -2 here out to, shit, I don't know, pretty far. The blue and the red are right next to each other. They start to disagree over here because I'm only using a finite number of terms. But if I had 1,000,000 terms here, this blue would stay glued to this red all the way out here. So this power series that we just worked with, x to the n over n factorial summed from 0, that's the power series for e to the x. We'll prove this later, right, next week. 2 more examples to show you, and then I'll let you go. Like I said, no dedicated lab time today. I'm going to run a little bit over our normal time, and then we'll just be done. Same bullshit. Find interval and radius of convergence. For the sum sigma n equals 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. When you're looking for the interval radius of convergence for a power series, you need to run the ratio test. Now, this doesn't look like a normal power series right away. It's not like x minus a to the n. All right, the power here is 2n plus 1. The first few terms of this series, just to write them out to help you see. When you plug in n equals 0, you get 1 over 1 times x to the 1. That's x. You plug in n equals 1, you get minus 1/3 x cubed. You plug in n equals 2, you get plus 1/5 x to the 5, then minus 1/7 x to the 7, plus 1/9 x to the 9, minus, and so on. So really what's going on here, if I asked you for the coefficients, Cn, it's not -1 to the n over 2n plus 1. It's actually more complicated than that because all the even coefficients are 0. And then if n is odd, then we get -1 to the k over 2k plus 1. If n is equal to 2k plus 1 is odd. The formula for the coefficients here is not obvious. But you'd think of this as 0 plus x plus 0x squared minus 1/3 x cubed plus 0x to the 4 plus 1/5 x to the 5. If you think about it and you need to put time into this, you'll realize that this formula for the coefficients is correct. And the center, well, everywhere you have a power of x here, it's just x to the 5, x to the 7. The center here is, again, 0. You don't have like x minus 1 to the 5, x minus 1 to the 7. So my center is 0, which means my interval of convergence is going to be symmetric about 0. And if I want to start finding the IOC, ROC, ratio test is the tool. L is the limit as n goes to infinity of an plus 1 over an, which is the limit as n goes to infinity, absolute value. So I just take all this shit, right? These are my an, the whole thing inside the sum. So an plus 1 is -1 to the n plus 1, x to the 2 times n plus 1 over 2 times n plus 1 plus 1. That is an plus 1. And I divide it by an. So I multiply by the reciprocal of an, which is 2n plus 1 over -1 to the n times x to the 2n plus 1. Algebra, even here in Calc 2, is the biggest hurdle, I think. Just making sure your algebra skills are sufficiently strong. So when it comes to this ratio test work, I want you guys to really take your time. Be very, very careful. It's easy to make mistakes. Are there any questions about where any of these pieces are coming from or why I'm writing them the way I am? Okay. This is equal to lim n to infinity. Again, we're going to shuffle the terms around to get the matching shit together. -1 to the n plus 1 over -1 to the n times x to the 2n plus 2 plus 1 is x to the 2n plus 3 over x to the 2n plus 1 times 2n plus 1 over 2 times n plus 1 is 2n plus 2 plus 1 is 2n plus 3 again. And those same tools, algebra tools to simplify, we use them again. So you must practice this. You divide -1 to the n plus 1 by -1 to the n, you get -1. You divide x to the 2n plus 3 by x to the 2n plus 1, again, you subtract powers. 2n plus 3 minus 2n plus 1 is 2. So this is x squared times 2n plus 1 over 2n plus 3, nothing to do there. And again, we can take the absolute values of each piece because they're all multiplied. This time, we get lim n to infinity, absolute value of x squared times 2n plus 1 over 2n plus 3. Again, the absolute value of x squared, this will pop out past the limit because it doesn't have any n's in it. I can pop the square out of the absolute value if I want to, it doesn't make a difference. And then what's left is lim n to infinity, 2n plus 1 over 2n plus 3. What is this limit? Good, again, this is 1. You could renormalize or use L'Hopital's rule or make the lead coefficient argument. It's 2n over 2n, or sorry, it's 2 over 2, the lead coefficient ratios, as the degrees match. Whatever argument you like, you get the absolute value of x squared times 1. Since L is equal to the absolute value of x squared times 1, the series will converge provided L is less than 1, which is equivalent to saying the absolute value of x squared is less than 1. A word of advice. When you have problems like this, where you get not just the absolute value of x or the absolute value of x minus 3 or something, you have a power, take the nth root at this stage. Don't try to unpack first. You'll get confused. So let's take the square root at this stage with the awareness that everything here is positive. I don't have to worry about my plus and minus, and the square root of 1 is 1. So this is equivalent again to saying that -1 is less than x is less than 1. So my center is 0. My radius of convergence is 1. All right. You get the radius. If I plug in anything from the interior here, this series will converge. But the question is, what happens at the end points? So endpoints. We must check these separately. At x equals -1, we get sigma n from 0 to infinity, -1 to the n times -1 to the 2n plus 1 over 2n plus 1. And my question for you is, what is -1 to the 2n plus 1? I claim that this piece is actually constant. This piece does not change with n. Focus on this for a second. Think along with me. What kind of numbers does 2n plus 1 spit out if you put in integers for n?
Purely odd ones.
Odd ones. Yeah. If I raise -1 to an odd power, what do I get?
Negative numbers.
Yeah, just -1. -1 to the 2n plus 1 is always -1. So here we have this negative no longer depends on n. This is negative sigma n from 0 to infinity, -1 to the n over 2n plus 1. So you plug in the endpoint, simplify as much as possible, and then you ask, does this series converge or diverge? Help me out. Good, it converges. Why? What test? Very good. The alternating series test will show me that this is a convergent series. The bn's here are 1 over 2n plus 1. So I'm getting some answers in DMs here. That's why you're not seeing them in the chat, but So -1 is a part of the IOC here. Right, I know that my IOC is either -1 to 1 closed, -1 to 1 left open, right closed, -1 to 1 left closed, right open, or -1 to 1 open. I knew that as soon as I got to here. And since I know -1 is a part of my IOC because the series does converge there, I can kick out anything that doesn't contain -1. That means this guy and this guy gotta go. To figure out which of the other two, I need to check the other endpoint. I need to check x equals 1. So if I plug in x equals +1, we get sigma n from 0 to infinity, -1 to the n times 1 to the 2n plus 1 over 2n plus 1. And 1 raised to any power, right? This is just the constant 1 raised to the 2n plus 1. That's always going to be 1. So this is sigma n from 0 to infinity, 1 to the n over 2n plus 1, which is just the positive version of the previous series. This also converges by the alternating series test. So my series converges at both -1 and +1. This IOC would say my series converges when you plug in -1, but does not converge when you plug in +1. So I can kick him out as well. Therefore, our IOC is the interval I equals closed, -1 to 1 closed. And that's it. So the interval of convergence for this series is closed interval -1 to 1. And the radius of convergence for the series is 1 because the center is 0. We actually saw this series before as well. I told you that when you plug 1 into this series, it spits out pi/4. We saw that somewhere else. Again, I'd like to look at partial sums really quick. So this was x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7 plus x to the 9 over 9 minus x to the 11 over 11 plus blah, blah, blah. Again, I want to play this game. So here is the kind of first partial sum, right? The next partial sum would be x minus x cubed over 3. The next would be that plus x to the 5 over 5. The next would be that minus x to the 7 over 7. This one converges pretty slowly. So I'm going to move. Oh, sorry, this needs to be a minus. I'll come all the way out here. Try and give you a little feel. Now, this looks kind of messy, right? If I just show you this last guy, you probably still won't be able to quite see it. Now you can. Look, between -1 and 1, my series and the blue partial sum and the red function are indistinguishable. Now the red function arctan, his domain is all real numbers, but this series only converges if x is between -1 and 1. That's why you're seeing this weird behavior outside of that interval. But if you focus just between -1 and 1, you see the blue getting closer and closer, closer to the red. And all the way out here, the order 15 partial sum between -1 and 1 is a very good approximation to the red function. So in particular, if you wanted to know the area from like 0 to 8/10 under the red function, you could find that area for the blue function instead, and you'd be pretty good. This is the power series for the inverse tangent function. It's a powerful tool. All right. Other important power series we're going to learn to work with: sine, cosine, natural log. Those are the big ones. E to the x, sine x, cos x, log x, arctan x. Those are the power series that next week I'm going to require you to commit to memory. I'll show you where these come from. It's actually not that hard to prove. It all kind of starts with geometric series. But in order to understand what we're doing, you will need to be comfortable finding intervals and radii of convergence. So that's what your task is between now and Tuesday. Your task is to work hard on this homework and make sure you are comfortable calculating intervals and radii of convergence. It's not that bad. Remember, the first thing you do, identify the center. Make sure you know what the center of your series is. Then run the ratio test. The ratio test will give you an inequality that you can solve to find the endpoints of your interval of convergence. That will also tell you your radius of convergence. Once you know the center and an endpoint, the distance between the two is the radius. Then you test each of the two endpoints, and that will tell you for sure exactly what your IOC is. That's it, lads and ladies. That's the game between now and Tuesday. And then next Tuesday, I'm going to start showing you how to find power series for a given function. Like I give you a function and tell you find the power series for this function. We will learn how to do that. And then Thursday of next week, we will learn how to solve some problems. To give you a little window of where we're going, recall that the integral of arctan x over x dx is impossible. So are like integral sine x over x dx and integral cos of x squared dx. These are all integrals at the beginning of the semester that we said no matter how good you get at integration, you just can't do it. There is no closed form for the antiderivative of these functions. You can smell where this is going. If I can find a big fucking polynomial representation for arctan, then I can divide that bitch by x and integrate it. That will give you an answer to this integral. If I can find a big, long, infinite polynomial, i.e. power series for the sine function, then I can divide that big, long polynomial by x and integrate that, because polynomials are easy to integrate. If I can find a polynomial or power series for cosine, I can swap in x squared everywhere there's an x and integrate that. That will give me an answer for each of these previously impossible integrals. It's a big deal. This is why we love power series. And this is why we've done all the work we've done since spring break on convergence. All of it is building up to this. So dump some time in, right? This is the absolute heart of the crunch of this class. Hopefully you're good at convergence testing now. Take that skill, apply it to power series, and you will be okay next week. The content we're covering next week is the hardest in the class. Once it's done, it's done. And then we'll move on. The last week here is going to be easy peasy stuff. It's parametric equations, it's some integrals. It's not that bad. But you need to get comfy with this power series stuff. This is where I draw the line in the sand. I say, you will not pass my Calc 2 unless you learn this shit. You can do it. You can do it. If you're in trouble, ask for help. I'm happy to help. But that's all. You put the time in, you'll get good. All right. Any burning questions before I let you guys go for today? Alrighty, work hard. The homework is open. It's not terribly long, and it's just 15 problems. So I made it short because each one of these is a quite lengthy procedure. Make sure you're comfortable. Remember, identify the center, then the ratio test, then test endpoints. No, Alejandro, it is not. So the true, false, and multiple choice questions, you don't need to give me any work for them. You just write the answer. You don't even need to write anything. Just click the correct answer. The only problems on exams that you're required to show work for are the free response problems. Other questions?
Have a great day, Professor.
You too, Ethan. All right, if there are no other questions, I am going to go ahead and end our thing here. I know we didn't have an office hour today. I had a meeting in place of that. I'll throw an extra office hour in next week to compensate. Hope you guys have a lovely rest of your day. And again, if you do have trouble with anything, don't hesitate to ask for help. Take care.
Bye. Bye-bye.